established Wi-Fi network. So when we talk of communication criteria, what and all are the characteristics by which we decide upon the technology that we want to use? First, very predominant one is the range. Range basically is the signal propagation or else the distance that we wish to cover. The next one is the frequency bands, whether you wish to use licensed frequency spectrum or else we want to use unlicensed frequency spectrum. We will be going in depth with coming slides in each of this. Then we have power consumption, whether the devices that we will be using will have a stable power supply or else it's going to be battery powered. Then what kind of a topology in which we want to rearrange or organize our devices. Then whether the devices are constrained devices, means do they have limitations in terms of computing capability or else in terms of storage ability. Then constraint networks itself. What kind of a network we wish to use. These are all some of the characteristics by which we decide upon the technology. Now moving on to some of the predominant technologies that are currently being used. One is IEEE 802.15.4. This actually is a PHY and MAC layer defined one. IEEE 802.15.4 G and E is an improvisation or some of the limitations of IEEE 802.15.4 was addressed in this. This IEEE 802.15.4 is not very directly used. Over that, we will have like Zigbee. Zigbee is a network and application defined protocol which works over IEEE 802.15.4. So the PHY layer and the data link layer that is defined in IEEE 802.15.4 is used as it is in Zigbee. Zigbee comes with the network layer and the application layer being defined. Zigbee formed an alliance of appliance manufacturers who developed devices which would be interoperable, but some other device which is not a Zigbee compliant one will not work with this. This was the drawback of Zigbee, because of which they tried to come up with a common network support 6-low-pan support, and that happens to be the Zigbee IP. Then we have IEEE 1901.2a. This is just used for connecting smart objects over power lines. Maybe the IEEE people would be more interested to venture into this because it would be more upon smart metering and things like that. Then, as we discussed, IEEE 802.11ah Wi-Fi that we call is IEEE 802.11, which has been very successful and extensively used everywhere. Then they came up with a standard so that they are able to even support devices. 802.11, that is Wi-Fi, works with 2.4 gigahertz band, but normally 2.4 gigahertz is a very short range, high data rate band. For IoT devices, if you are going to use a band like that, it might provide you with a higher data rate, but actually you don't need such big, huge data rate for IoT, first thing. Second is you would expect a little decent distance of coverage, uh, which is not provided with 2.4 gigahertz. So there is a new band on which it works. We will look at it going further. Then we have LoRaWAN, and the other one is narrow band IoT and LTE variants. Basically, this narrow band IoT and LTE are for long distance communication. So when we talk of range of connectivity, short range, medium range, long range, we have Bluetooth as well as visible light. If or else infrared that we say, this is what is used for our remote. That is the shortest range. We have Zigbee 802.15.4, 802.15.4 GE as the mid-range uh, devices technology which is able to cover that distance. And we have Wi-Fi and this LTE being able to have a much longer distance. What actually is the distance? We'll look at it here. Short distance, basically Bluetooth as well as visible light communication. IEEE 802.15.1 is Bluetooth. IEEE 802.15.7 is visible light. That actually is not mature enough for production deployment. It is used for standalone simple applications like your TV remote and things like that. Then you have medium range devices, which consists of some tens to 100 meters. Maximum distance of less than, basically it is less than symbol, which has got misprinted. 1 mile between any two devices. And some of the technologies which work in that is IEEE 802.11 Wi-Fi, IEEE 802.15.4, and the improvement over that. Then we have long range, which is greater than 1 mile. Your cellular WiMAX, narrowband IoT, all this outdoor IEEE access point also works with longer range distance. Basically, before venturing into doing things, we are supposed to do radio planning, which basically means you need to do a field survey. How many devices would suffice to cover a particular region, or else what actually is the range of the device and how much where how optimally you can place them. When we talk of frequency bands, uh, it's regulated by International Telecommunications Union and the Federal Communications Commission. Basically, they decide upon what spectrum to use for what purpose globally. That is when devices which are uh, they can interoperate. Second is the frequency is classified into licensed and unlicensed bands. License band is one for which if you are planning to use your devices, then you are supposed to subscribe for the services provided by the service provider. Let it be the your mobile phone service provider or some other service provider like cellular, WiMAX and narrowband IoT. All this comes under this license spectrum. Then we have unlicensed spectrum, which actually is free of cost, uh, which has been classified as industrial, scientific and medical applications. For this, these spectrums can be used. 2.4 gigahertz that we use for Wi-Fi is one such unlicensed spectrum. Even IEEE 802.15.1 Bluetooth as well as IEEE 802.15.4 works upon unlicensed spectrum. As we discussed in the unlicensed band, again, unlicensed band doesn't mean that it is not regulated. Okay, it just means that you don't need to pay for it. Regulations are mandated by each country where the devices are sold. Regulations basically mandate upon what can be the maximum transmit power, the duty cycle, dwell time, channel bandwidth, and the channel hopping sequences that are possible. Basically, as I told you before, one is 2.4 gigahertz gives you a higher data rate, but with a shorter range. Second is since Wi-Fi is very predominantly used in that, for IoT, this was not seen as a very prospective band. So there is something called as a sub gigahertz frequency band, which actually aptly suits for IoT applications, which is able to penetrate through infrastructures relatively better than 2.4 gigahertz. The weakness of sub gigahertz is the data rate is relatively lesser. Anyhow, for IoT devices, we wouldn't need the data rate as much as we expect for a Wi-Fi based ones. This sub gigahertz band ranges in about 169 megahertz, 433 megahertz, 868 megahertz and 915 megahertz. This 868 and 916 I have uh, uh, highlighted because that's very predominantly used with uh, Zigbee and many other WPAN technologies. EIRP basically is effective isotropic radio power. It is basically the amount of power that an antenna would emit to produce peak power density. And duty cycle is the percentage of time a device can be active in transmission. These are some terminologies that are very effectively used in devices, which you need to know. As I told you, 868 megahertz band is used by IEEE 802.15.4, 802.11ah, and also LoRaWAN. All these WPAN technologies are using this band. So basically, we are supposed to note that frequencies and corresponding regulations of a country are supposed to be considered before implementing or deploying the IoT smart objects. Now, coming on to the next parameter, one is the power consumption. Whether the nodes are battery powered or else direct, do the nodes or devices have direct connection to a power source? Battery powered devices would provide you with more flexibility because you can move around with the device, but it would also demand upon the technology to optimize power consumption. Then we have topology. There is three topologies that are prevalent. One is called the star, second is the mesh, and the other one is the peer-to-peer. Most of our Wi-Fi is star topology based, where it's suitable for long range communication, and you will have a central base station. Then you have peer-to-peer topology, in which every node would be able to communicate with every other node with a one hop communication. Mesh topology basically, in order to have a long distance communication, you would try to have one node acting as intermediate one, which actually forwards the frames or data. That way, mesh topology is a complex formation of peer-to-peer topology. This actually is an example um, for it. Star topology, where you have one base station which is able to communicate. Peer-to-peer topology, where every node is able to address every other node and communicate. Whereas mesh is a combination, or it is a extension of peer-to-peer and star. There are certain properties for each of this topology. Mesh topology would be able to optimize with trying to reduce power consumption as much as possible and increase overall distance. Try to cover as much as distance via certain nodes. That's what is mesh. If you would see in the figure, there are two types of devices. One is called as the full function device, which actually will have relatively better resources, and it will try to actually connect other devices. And the other one is the reduced function device, which can only act as a leaf node or the last point connection. Leaf node or reduced function device. So now the next one is the constrained devices and unconstrained devices or nodes. Unconstrained nodes are things like server, desktop, laptop, smartphones, which have uh, directly connected power source. Then we have constrained nodes, which are classified into different types called as class A, class 0, class 1, and class 2, based upon the resources that it has. Limited resources with limited networking feature is what is a constrained node. So class 0 is a device which will have less than 10 KB of memory and about 100 KB of flash. The previous 10 KB is RAM storage and 100 KB is the flash storage. An example is like a push button, which would actually just try transmitting 1 byte of data upon status change. The second one is the class 1, which falls in between class 0 and class 2. There is no clear demarcation for it. The only thing is it would not have enough memory to embed the complete functionality of full IP stack. It might have a reduced optimized stack like the constrained application protocol stack installed in it so that it's able to operate or communicate with class 2 devices. Class 2 is the devices that have more than 50 KB of memory and 250 KB of flash memory, which can run a full IP stack. So these devices come under class 2. We also described that constrained node networks. Basically, very commonly constrained node networks are called as uh, low power lossy networks, LLNs, in which lossy networks indicates that the network performance is more vulnerable or susceptible to interference and variability due to harsh radio environments. Low power because obviously the devices that are connected to it do not have, they are all constrained nodes. Some of the important parameters for that determines these things are: one is data rate and throughput. In a WPAN network, the data rate ranges from 100 bits per second to 10 Mbps. In 10 Mbps basically is provided by LTE and IEEE 802.11 AC. In general, in any IoT network, if you would see or observe, upstream traffic towards application server is usually more than downstream traffic from the application server. After all, devices are used to sense and communicate those details up. Maybe after analysis, analytics and all, actuators might receive certain commands, but the amount of data that is driven upside would be always more. Latency and determinism are some of the parameters that are supposed to be considered, which can range from few milliseconds to seconds. Overhead and payload, basically IPv6 maximum transferable unit MTU size is about 1280 bytes, whereas the payload size for IEEE 802.15.4 is about 127 bytes. So because you would have IP frame packet which needs to work via your data link frames. So these IP v6 packets are supposed to be fragmented. So fragmentation is a very mandatory thing so that you are able to have this interoperability working. With IEEE 802.15.4G, they have been able to improvise upon the payload of the data link layer to 2048 bytes. Thus, they are able to avoid this fragmentation and reassembly that is mandated with the basic protocol. Payload basically is the data part that we send. In LoRaWAN network, the payload can be as little as 19 bytes, or it can go up to 250 bytes. Now let us move on to IEEE 802.15.4. Basically, this is a very the file layer and the data link layer is being used by so many protocols. One is Zigbee uses this. IEEE 802.11 AH uses this. LoRaWAN also uses this. So this is a wireless access technology which basically defines the file layer and the data link layer for low cost, low data rate devices that can be powered on batteries. The ease of installation and simplicity are the strengths of it. And the protocol stack is relatively smaller in terms of memory memory print. This is predominantly used in home and building automation, automotive networks, industrial wireless sensor networks, and many such small networking applications. This is predominantly used. What are the weakness of IEEE 802.15.4? One is it uses CSMA-CA, carrier sense multiple access with collision avoidance. If you would have studied CSMA-CA, it's actually a access control, multiple access control protocol, which allows which allows to send data if there is the data is not received, it tries to have a back off. Because of this, the MAC becomes unreliable, and also you cannot provide it with a bounded latency. The latency cannot be predicted or guaranteed. And also this IEEE 802.15.4 is susceptible to interference and multipath fading. These are all overcome with the next version of the protocol. We will look at it as we go further. Yeah, interference and multipath fading occurs because IEEE 802.15.4 doesn't employ frequency hopping technique. It just works upon one frequency, because of which uh, uh, interference as well as multipath fading can happen. What's basically multipath fading? When you send a signal, there can be it suffers from interference and multipath fading because it doesn't support frequency hopping technique, which has been addressed later with the improved versions, which we'll see. This basically is defining the phi and the MAC layer for WPAN. These are the other wireless technologies that are very predominantly used. One is Zigbee, Zigbee IP. 6LoWPAN basically is a layer 3 protocol that is used by Zigbee IP. Then we have wireless HART and Thread. So now let us move on to the Zigbee protocol a little bit more in detail about it. Basically, Zigbee is very predominantly used protocol in the WPAN segment. It has about 400 companies who are members of the Zigbee Alliance, which certifies for the interoperability between the vendors. It is used for sensing temperature, humidity, and things like that. It's also used for home automation, for lighting control, thermostats, and security functions. A set of basically Zigbee Smart Energy helps in monitoring as well as controlling the energy utilization. There are different application profiles that are defined in Zigbee, which happens to be the building block. Clusters are a set of commands and messages that are defined for different functions in a device. Interoperability is one of the strengths of Zigbee, and it is built over IEEE 802.15.4. This is the protocol stack As you could see, the PHY layer as well as the MAC layer is the prevalent one, IEEE 802.15.4. Then actually the Zigbee platform is able to define the application support as well as network and security layer support. And applications or profiles are like, as I told you, energy profile, home automation profile, things like that, which are specifically designed for specific applications. These are some of the characteristics of the Zigbee protocol or technology. It supports network setup, configuration, routing, and secure communication. It's able to calculate routes, discover neighbors, and manage the routing tables. It predominantly supports mesh topology, but is not just limited to that, but it's also able to support star and tree. It uses advanced encryption standard with 128-bit as the security at the network as well as application layers. Zigbee is based upon advanced on-demand distance vector routing, which actually is a reactive routing protocol. Whenever there is data or packets that are supposed to be sent, the routing table is searched. If there is no path, only then the discovery process is initiated. The disadvantage of Zigbee is it is interoperable only with devices which are Zigbee compliant. Because of these limitations, Zigbee IP came into existence. Zigbee IP is built over 6LoWPAN as an adaptation layer at layer 3. It was initially seen as or designed for smart energy profile, but with time it has become a generic standard. So basically all Zigbee IP nodes are able to support IPv6, ICMPv6, neighbor discovery, and see, like how Zigbee was working upon AODV, this works on routing protocol for lossy networks, RPL, as the routing. It's also able to support transport layer protocols like TCP, UDP, both connection oriented as well as connectionless. Zigbee IP is able to integrate and interoperate with just any other device which works over 802.15.4. This is the protocol stack for Zigbee IP. As you could see, the MAC layer and PHY layer is the same. Maybe it is advanced version with released later on in 2006. Adaptation layer 6LoWPAN is placed. Then over that there is support with IPv6, ICMP, neighbor discovery and other things, and also transport layer. So these are the difference between Zigbee and Zigbee IP. these three layers, transport layer, network layer, and 6-lopan adaptation layer was not available. So when we look at the physical 5-layer of Zigbee IP, it uses direct sequence spread spectrum as the modulation technique. These are some of the 5-layer transmission options with 2.4 gigahertz also being supported with 16 channels with a data rate of about 250 kbps. 915 and 868 are the common sub-gigahertz frequencies, which are supported with a data rate of about 40 and 20 respectively. With, as I told you, the improved version of IEEE 802.15.4, which got revised to 15.4-2006, and also IEEE 802.15.4-2011 and IEEE 802.15.4-2015. These things have been able to support additional 5 options, 5-layer options. One is the offset quadrature phase shift keying as one of the modulation technique. Other one is binary phase shift keying and amplitude shift keying. So these are the additions that are done. With these improvements that have been put up with IEEE 802.15.4, it has resulted in the data rate being increased to about 100 to 250 kbps. This is the 5-layer format for Zigbee IP, where you have a preamble and a start frame delimiter. The preamble is of about 4 bytes, whereas the start frame delimiter is about 1 byte, which is used for synchronization. Frame length is about 1 byte, which actually hints upon the size of the 5 service data unit, PSDU. The maximum size of a PSDU is about 127 bytes. Which would enforce that fragmentation has to be done when it's being passed on from the network layer. The MAC layer of Zigbee IP performs these tasks. One is network beckoning, which would act as coordinators. Then you have a PAN ID being assigned to each of the personal area network formed with a Zigbee with one coordinator. So PAN association as well as disassociation is performed by the coordinator. Device security as well as reliability is maintained between any two MAC entities, which basically is the default function of MAC layer. These are some of the MAC frame types that is supported in 802.15.4. One is the data frame, which is used to send payload. The next one is the beacon frame, which is transmitted by the PAN coordinator. Then we have acknowledgement frame that confirms the successful reception of a frame. Then we have MAC command frame, which is responsible for the control communication between the devices. This is the MAC frame format of IEEE 802.15.4. It consists of a frame control, which is about 2 bytes, which contains or hints upon the frame type, addressing modes, and other control flags. The sequence number is able to uniquely identify the frame. Addressing fields are used to identify the devices between whom the communication happens. As you can see, the payload part in the 5 frame happens to be the complete MAC frame, as shown in the figure. This actually is MAC frame format with auxiliary security header being added. In the frame control, there is a bit for which hints upon whether security is enabled or not. So if that bit is set to 1, then this field of auxiliary security header will be added, which will steal some of the bytes from the frame payload length. It supports 64-bit extended MAC address, which is based upon Ieee 64 standard addressing. Since the address size is long, there is also a provision of 16-bit short addresses being assigned to devices. But this 16-bit short addresses are local to a personal area network, which would limit its communication capabilities beyond the network layer or the transport layer. This figure shows that IEEE 802.15.4 supports mesh topology. As you could see, there can be only one PAN coordinator among the nodes which have full function. Among the full function devices, one device would be elected as a PAN coordinator. As we discussed previously, the devices with limited capacity would form as the leaf nodes, which would be the reduced function devices, whereas devices with relatively better storage as well as computational capability would be full function device, which can store the complete IP layer footprint. Basically, these terms mesh under and mesh over, the data communication that is done over with the data link layer is called as mesh under. If the communication is being done over IP layer, that is 6 low pan adaptation layer. Above that, then that is the data transmission is called as mesh under, mesh over. Security in IEEE 802.15.4 is able to support advanced encryption standard with 128-bit key length. That AES standard that is used in 802.15.4 not only validates the data that is sent, but also the message integrity code that is calculated over the entire frame using the same AES would also it would be able to help us in checking whether there has been any integrity violation that has happened in between. As I discussed, IEEE 802.15.4 is a improvisation over IEEE 802.15.4, which is able to improve upon the reliability, bounded. It actually is able to break the unbounded latency, basically latency, and multipath fading. It's able to use frequency hopping so that it's able to secure the improve the security, and it also supports secure acknowledgement and secure enhanced beacon feed. So with that, we complete Zigbee and Zigbee IP. This is just to touch upon IEEE 802.11ah, which actually is a following standard from IEEE 802.11 Wi-Fi, which has been very prevalent and very successful. IEEE 802.11 is even now used for most of the fog computing, high data rate sensors, audio and video analytic devices, and also to deploy backhaul infrastructures. For all this, IEEE 802.11 is being used. The only drawback of Wi-Fi is it does not support sub-gigahertz frequencies. Sub-gigahertz, as we discussed before also, is able to provide us with longer connectivity, but with a relatively lesser data rate. But it's also able to support a large number of devices, which is not possible with IEEE 802.11. So they worked, a work group worked upon it, and they came up with IEEE 802.11ah, which is called as Wi-Fi Halo. Wi-Fi Halo or IEEE 802.11ah works in the sub-gigahertz frequency bands. And it operates in these frequencies. It is based upon orthogonal frequency division multiplexing, modulation, and it uses the following channels 2, 4, 6 or 8 megahertz. The data rate is about 100 kbps, and the transmission range is about 0.62 miles. These are some of the 5-layer characteristics. When we look at IEEE 802.11 MAC layer, MAC layer supports the new sub-gigahertz Wi-Fi 5. It's able to operate at low power consumption, and it's able to support a large number of endpoints to be connected. If you would look at IEEE 802.11, it connects about 512 or 1024 end devices, whereas this is able to connect as much as 8192 end nodes. The MAC layer is also shortened so that the communication is more efficient. These are some of the salient features of IEEE 802.11 One is null data packet support. By enabling null data packet support, control frames, data frames, manage acknowledgement frames need not have to be completely different. It's able to support with the same. Grouping and sectorization. The antennas can be sectorized so that it's able to cover a particular set of region, because of which collision or contention is relatively reduced. Restricted access window. By restricted access window, you are able to allow data. It's a way of optimizing frame transmission such that contention time is not every time pulling your throughput down. Speed frame exchange, target wake up time, and it supports star topology. Just like how IEEE 802.11 also supports star topology. So with this, I come to the end of the session today. If you have any doubts, you can please ask now.
Dear participants, if you have any queries, you can ask, sir. You can type in chat box, or you can unmute your mic and you can discuss. Participants, any queries? Sir, I think no queries, sir.
Okay, madam, then let us complete the session. Yeah.
So I have one doubt.
Yes, please go ahead.
Okay.
Sir, in device to device communication, is there any third party involved? When one device
what do you mean by third party? Basically, that is what first thing is, there are too many technologies which work in device to device communication, out of which some prominent players are Zigbee, this LoRaWAN, and these things. Okay, third party means, what do you mean by that? If you are not very sure that you will be using one technology, then it is better you go for Zigbee IP, which will work with any other technology also to
Okay,
make
so
things more interoperable to work with third party or other vendor devices. Zigbee has improved it with Zigbee IP, which has made it more interoperable. Yeah.
means somewhere na I read like this ki in device to device communication there will be no any other third device is required for communication. So means at that time I don't understand what they want to say. That's why I'm asking you ki in device to device communication is any other server is there which help to communicate between these two devices.
See, whether it depends upon your network configuration. First thing is, if you are just going to have one gateway and that gateway is a high-end system, then it will be a one-hop communication. That's all.
Okay.
If you want a network configuration where it's like a mesh topology, where there can be many forwarding being done by nodes, then it needs a intermediate devices which would forward.
Okay.
That is possible, yeah.
And can you suggest any simulator which will use to perform some deploy some security algorithm like AES and DES, as you said, or ECC on the devices and to execute all on the simulator only? Is it possible?
Why do you want a simulator, madam? You can still go for a real-time use case scenario. No, you just need Zigbee modules. That's all.
Okay, on Raspberry Pi, on Arduino also we can execute elliptic.
Yes. With Arduino you can do. Raspberry becomes a full device basically.
Right, it have all power.
Correct. So I would better suggest that try doing that way than a simulator. That would give you a practically real experience, and also your data would be realistic.
Okay, thank you, sir.
Sir, one question is there in the chat box, sir. Which tool is used for implementation?
What implementation basically? See, if you wish to have this stack is already a open source software that is available. You just need to actually interface it and write it onto your end device. See, there are certain there is something called as a JTAG ICE, which is used to burn images of software or firmware onto devices. Again, it depends. With current technology, I think even with a USB port, you can actually copy directly. So I don't think there is any tool specifically being used for it.
Participants, any other queries? Sir, there is no queries, I think, sir. Can we conclude?
Okay, madam. Yes, we can conclude.
Okay, sir.
Yeah.
Good evening to one and all present here. On behalf of Computer Science Engineering, NIT Puducherry, I thank Dr. Narendra Rajagopalan sir for his patience and time to share his knowledge to the participants. Thank you so much, sir.
Thank you. It was my pleasure.
Thank you, sir. Thank you.